Oh, class. Okay, so we're going to talk about heat and internal energy. Now, heat is a very common word that's used in everyday language, but we have to be careful about what this means in physics. So, again, say we have two objects that are in thermal contact with each other. And let's say A is at a higher temperature than B. And just say TH for hot, TC for cold. And if they're in thermal contact with each other, energy is going to flow from A to B. And we call that energy that flows because of a difference in temperature. You know, I mean, you put them in thermal contact, this is just going to happen spontaneously. You know, we're not like, there's other ways of exchanging energy between objects. You could do work on them. But this is a spontaneous flow of energy, and we call that heat. And so, again, this word might have, you know, just because we use it in common language, it would be easy to kind of use it incorrectly in physics. Like, say you have a cup of boiling water, you know, it might sound right, it's boiling water, it might sound right to say this cup contains a lot of heat, but that is not the correct way to use the word. Heat is a transfer of energy, and so what we would say instead is that this cup of water contains a lot of internal energy. So what is internal energy? Basically you look at say water, or you know, it could be anything, but in this example it's water. It's molecules, H2O. So there's these molecules in here, and they're moving around, and there could be interactions between molecules that have potential energy. But in general, the internal energy is the sum of all the energy of the parts of the system. Like in this case, the sum of the energy of every molecule. In the cup of water, that's its internal energy. So the cup can have a lot of internal energy, but we wouldn't say it has a lot of heat. And so again, heat, temperature, these are words that are very commonly used, but we have to be a little careful in physics. So let's look at another example of you know, how it could be misused. Let's say we have a cup of boiling water and say a tub of room temperature water. Now, which of these has more energy? Well, the room temperature water, like a tub of water, room temperature, would have more energy than just like a cup of boiling water, just because there's so much more water in the tub. So like the individual molecules here are very energetic, where here, not so much, but there's more of them. And so again, that's why it would be kind of misleading if we mistook, or if we misused heat and internal energy, because this is clearly hotter, but yeah, if we said this cup has more heat, or you know, we could correctly say that this tub has more internal energy than the cup of boiling water. But it would sound kind of strange if you said that this tub of water has more heat than the the small cup of boiling water. So yeah, just we have to be a little bit careful about the words that we use. So temperature, again, that's you know, an indication of which object, like which way the energy is going to flow. Temperatures, the energy flows from hot objects to cooler objects. Heat is that energy that flows, and internal energy is just a measure of how much energy is in the system. Take a look at the microscopic level, all the parts of the system, add up all the energies, that's the internal energy. Okay, now, how do we measure these things? Well, historically, they did not know about atoms back in the 1800s. And if you look at this process, if you have these two objects that are at different temperatures, one's hotter than the other, of course they noticed that something was happening here. This object would cool off, this one would warm up. Like if you touch something hot, obviously, you're going to feel that full of energy. But they didn't know what it was. And so they assumed that it was a fluid, that there's an actual fluid flowing between these objects. And they called it caloric, I believe. Let me see if I'm spelling that right. What did they call that? Yeah, caloric. And there was actually, it's not a bad theory to think that there's some actual fluid that flows from one object to another. And one thing they cited as evidence for that is that when you heat things up, they tend to expand. It's like you're adding something to it, it gets bigger. Made sense. And so they gave it a unit called the calorie. So we used to measure this idea of heat in calories, and actually we still do in some cases. But this fluid theory of heat was eventually replaced. Actually, even before the existence of atoms was fully demonstrated, I believe. Yeah, I'm trying to look up the date. Yeah, there was an experiment that was a very nice experiment that was done by a guy named James Joule. Sorry. James Joule. And I can show you a picture of the experiment. I'm going to hold up this book. Yeah, it's in the textbook for the class. I don't have a physical copy, so I can't hold that up. But basically, you've got these two heavy masses that are connected by pulleys to this rod that, like as the mass, basically you release it and the masses fall and turn that rod, which has these paddles in a bucket of water. And so there's work being done on the system by gravity. And what James Joule was able to do, he wasn't the first to propose this idea that there was an equivalence between like mechanical work and heat and internal energy, but he was the one that did the experiment that could show kind of like how, very precisely, how this work done is actually converted into internal energy. He was able to do that very precisely. It's kind of interesting here. He did this in 1850, and his result only differs by 1% from the modern value. So anyways, he had this experiment with these wheels that dropped, and what he found is that, these wheels falling, they're falling at a constant speed. He set up the experiment so they fall at a constant speed. I'll draw a very inadequate picture here. So we've got this bucket full of water. Here's these paddles. So of course when this spins, these paddles are pushing the water around. And yeah, we've got these. These masses are falling at a constant speed. And so their kinetic energy is not increasing. Their potential energy, though, is decreasing. So potential energy is decreasing, and the water is heating up at the same time. And Joule's able to show by the amount that this heated up, he was able to show that he was able to come up with a conversion factor between calories and our kind of modern system. Normally we measure energy in joules. Actually, it wasn't done that way in James Joule's time, but we named the unit after him. And he was able to determine that 1 joule, at least in our modern units, which I think it's 4.186 calories. Yeah, the term calorie, it was used for heat, back before Joule did his experiment. And it stuck around because we use this for food. And so a calorie, basically 1 joule, 4.186 calories, or I think I actually got that backwards. Sure, I don't use calories often. They're kind of an obsolete unit. Yeah, I got that backwards. 1 calorie is 4.186 joule. Now remember, a joule is not a very big unit of energy. And, like if you lift a 1 kilogram object up a distance of 1 meter, the work you do is 1 joule. It's not that much, that would be 10 joules. We're going to take gravity into account. Yeah, the work you would do is mgh. So yeah, if you lift a 1 kilogram object up a height of 1 meter, that would be around 10 joules. So not that, it's not a huge amount of energy, 1 joule. And this might look a little strange if 1 calorie is 4.186 joules. The only time we really use calories is in describing food. If you eat food, it contains a certain amount of calories. And because this is such a small number, like food actually contains a lot of energy, when you see calories in food, they're actually kilocalories. So like for food, I think they use a capital C, is 4,186 joules. So, much larger number there. But, this was a very important experiment because it showed that heat is just a form, it's measured in joules. And it's not like some fluid or an actual substance. It's all related to energy. And so the idea is, what's happening is when these wheels fall, they're causing motion like this. The water is going to swirl around. You can heat it up, and the molecules can just become more energetic. And so, it tends to be like hotter objects. The internal parts, like the atoms or molecules, are just more energetic. Okay, and we're going to talk about what happens when heat flows from, like, say, into or out of an object. But we're going to do that in a separate video. So here we're just kind of defining these terms and showing that heat is a form of energy. But talking about what happens when you actually add heat or remove heat from an object, that'll be a separate video. So that'll be it for now.